All right, the first example we're going to do is problem 7 from section 5.7. It gives us the initial matrix 5, 0, minus 6, 2 minus 1 minus 2, 4 minus 2 minus 4, and the initial condition 2, 1, 0. It wants us to find the fundamental matrix and a solution that satisfies our initial condition. The first thing we're going to do is find the eigenvalues and eigenvectors of this matrix, which we will do by using A minus lambda I. From this, we get the characteristic equation minus lambda cubed plus lambda, which gives us eigenvalues lambda equals 0, lambda equals 1, and lambda equals minus 1. We'll find the eigenvector for lambda equals 1 first. Again, doing A minus lambda I. This will give us our new matrix 6, 0, minus 6, 2, 0, minus 2, 4 minus 2 minus 3. After doing some row operations to get this in upward triangular form, we get that our new matrix is 1, 0, minus 1, 0, 1, minus 1 half, 0, 0, 0. We now want to put this back in the form of a system so we can get our eigenvector, and that system is going to be x minus z and y minus 1 half z. So then we are able to find that x is equal to t, y is equal to 1 half t, and z is equal to t. So our first eigenvector will just be t, 1 half t, t. We'll then factor out a t, so we're left with 1, 1 half 1 times t. And we can now write our first entry in our fundamental matrix, which is x1 of t is equal to our first eigenvector times e to the corresponding eigenvalue times t, which in our case is 2, 1, 2. I multiplied by 2 here, by the way, just to get rid of that fraction, times e to the negative 1t, which simplifies to 2 e to the minus t, e to the minus t, 2 e to the minus t. We do this for each of our eigenvalues, but in the sake of time, I'm just going to write the other entries for our fundamental matrix. So for lambda equals 0, our fundamental matrix entry is x2 of t equals 6, 2, 5. The reason there's no e to the t terms in here is because our eigenvalue is 0, so e to the 0 is just 1, so it cancels out. And for lambda equals 1, our third and final entry is 3 e to the t, e to the t, 2e to the t. And now the fundamental matrix, capital phi of t, is just those three entries in a 3 by 3 matrix, which looks like this: 2e to the minus t, 6, 3e to the t, e to the minus t, 2, e to the t, 2e to the minus t, 5, and 2e to the t. We now want to evaluate this at 0, which is 2, 6, 3, 1, 2, 1, 2, 5, 2. It's also important to note that the determinant of this is negative 1, and it's not equal to 0. We now are going to find our inverse matrix, which is given by a to the minus 1 equals 1 over this triangle, with all our entries like this. All right. Right now I'm going to use a method that the book does not show. It's the method of minors and cofactors. I saw this method on Khan Academy. I think it's a little easier than what the book does, but it is a lot easier to make arithmetic errors. We're first going to find our matrix of minors, and we're going to use the simple format of Mij. And basically, for our first entry of what we're going to do is we're going to do M, which is our matrix of minors, of row 1, column 1. And basically what you do here is we look at our fundamental matrix that's evaluated at 0, and we cover up the I and the J row and column to build a 2 by 2 matrix here. So in this case, it's going to be 2, 1, 5, 2, after we cover up the first row and first column of our fundamental matrix that was evaluated at 0. And we get that the determinant of this 2 by 2 matrix is -1. We then do this 8 more times to build an entire 3 by 3 matrix. Okay, so our matrix of minors ends up being -1, 0, 1, -3, -2, -2, 0, -1, -2. Now, we want to turn this into our matrix of cofactors. And to do this, we multiply our matrix of minors by +1, -1, +1, -1, +1, -1, +1, -1, +1. So we get that our matrix of cofactors is -1, 0, 1, 3, -2, 2, 0, 1, -2. We also need to transpose this matrix, and once we do that, we get -1, 3, 0, 0, -2, 1, 1, 2, -2. So now we can write that the final inverse matrix that was evaluated at 0 is -1, 3, 0, 0, -2, 1, 1, 2, -2. And now we can write our final solution that satisfies our initial conditions, which is given by the form the fundamental matrix of T times the inverse fundamental matrix evaluated at 0 times our initial condition, which in our case will be 12e to the t, 6, 3e to the t, e to the minus t, 2, e to the t, 2e to the minus t, 5, and 2e to the t. I skipped a lot of steps here in this last part, but basically what you do is multiply the fundamental matrix times the inverse fundamental matrix times our initial conditions, which gives us this answer.